Hello everyone, today we will learn about power functions. Previously, we have studied the concept of functions. By utilizing the concept of functions and observing graphs, we have explored some properties of functions. Today, we will apply this knowledge to study a new class of functions. First, let's look at the following examples. Question 1. If Zhang Hong buys W kilograms of a certain vegetable at a price of 1 yuan per kilogram, then he needs to pay P, which is equal to W yuan. Here, P is a function of W. Second, if the side length of a square is a, then the area of the square, S, is equal to a squared, where S is a function of A. Example 3, if the edge length of a cube is B, then the volume of the cube V is equal to B cubed, where V is a function of B. Number 4. If the area of a square field is S, then the side length C of this square is equal to the square root of S. Here, C is a function of S. Last one. If someone travels 1,000 meters by bicycle within t seconds, then his average speed v while cycling is equal to 1 kilometer per second divided by t, where v is a function of t. Please observe the analytical expressions of these 5 functions. From the structural characteristics of the analytical expressions, what commonalities do they share? The square root of s in the fourth analytical expression can be represented as 1/2 root of s. Regarding the transformation of this representation, we will learn it later. In addition, the first analytical expression p equals w can be written as p equals w to the first power. The fifth analytical expression v equals 1 of t can be written as v equals t to the negative first power. Through observation, it can be found that these analytical expressions all take the form of a power. The base of the power is the independent variable, and the exponent is a constant. That is, they can all be written in the form of y equals x to the power of alpha, where the base is the independent variable and the exponent is a constant. Generally, we call a function of the form y equals x to the power of alpha a power function, where x is the independent variable and alpha is a constant. Now that everyone has understood the concept of power function, can you give some examples of power functions? There are many examples like this. For example, y equals x to the fourth power, y equals x to the negative fourth power, y equals x to the fourth power over 5, and so on. Please note that the exponent of a power can not only be an integer, but also other real numbers like 4/5. When the exponent takes other real numbers, the corresponding powers also have their respective meanings, which we will learn later. For the power function y equal alpha power of x, we only study the graphs and properties when alpha equals 1, 2, 3, 1/2, and -1. Next, please consider the general approach to studying a class of functions, drawing on your experience from learning linear, quadratic, and inverse proportional functions in junior high school, as well as the function knowledge you have acquired previously. Firstly, by abstracting examples from daily life, we derive the concept of a certain type of function. Then, based on the analytical expression of the function, we determine its domain and plot its graph. During the plotting process, we can utilize the point plotting method learned in junior high school. Then, based on the graph and analytical expression of the function, discuss its properties such as the range, monotonicity, and parity. Subsequently, utilize the graph and properties of the function to solve related application problems. Okay, following the general path of studying functions, it's time to graph the power function. Regarding these 5 power functions, we are familiar with y equals x squared, and y equals x to the power of -1. Please draw their graphs in a coordinate system and summarize their properties. Okay, let's analyze one by one. First, let's look at y equals x. This is a linear function, and its graph is a straight line. We know 2 points determine a straight line, so I'll take 2 points. 0, 0, 1, 1. Draw the corresponding image based on the given points. Okay, next let's examine the properties of y based on its graph and analytical expression where y equals x. Its domain is R, and its range is also R. It is an odd function, and it is monotonically increasing on R. Okay, next let's analyze y equals x squared. This is a quadratic function, which has excellent symmetry. When we take points, we can do so symmetrically. Let x be equal to -2, -1, 0, 1, and 2, respectively. The corresponding function values are 4, 1, 0, 1, and 4, respectively. Plot the corresponding graph by plotting the points. By observing the graph and analytical expression of y equal to x squared, we can determine that its domain is R, and its range is the interval from 0 to positive infinity, which is closed on the left and open on the right. It is an even function in terms of its parity, and it is monotonically decreasing on the interval from negative infinity to 0, which is open on the left and closed on the right, and monotonically increasing on the interval from 0 to positive infinity, which is closed on the left and open on the right. Next, we will analyze that y is equal to the negative power of x. This is an inverse proportional function graph, which is symmetric about the origin. Therefore, when taking points, we can also take them symmetrically. X is equal to -2, -1, -half, -1/3, 1/3, half, 1, 2 respectively. The corresponding function values are -half, -1, -2, -3, 3, 2, 1, and half. Then draw the corresponding image by tracing points. By observing the graph and analytical expression of y being equal to the negative power of x, we can know that its locality and value range are both open intervals from negative infinity to 0, and from 0 to positive infinity. Its parity is an odd function, and its monotonicity monotonically decreases over the open interval from negative infinity to 0, and also monotonically decreases over the open interval from 0 to positive infinity. We have now analyzed the graphs and properties of three familiar functions. Next, please think about how to draw an image where y equals x to the third power and y equals x to the second power. Let's first observe the analytical expressions of these two functions. Can you explain some of their properties? We don't have to say that the definition of y equal to the cube of x is r. We know that the first three functions have good symmetry, so is y equal to the cube of x symmetric about the y-axis or about the origin? Or, what is its parity? Let's verify it. If fx is equal to the third power of x, then f negative x is equal to the third power of negative x, that is, the third power of negative x. That is, negative fx, so we get f negative x equals negative fx. Furthermore, we can determine that y is an odd function equal to x3 power. The image is symmetrical about the origin, so we can take points symmetrically. But please note that since we need to draw 5 function graphs in a coordinate system, when taking points, in addition to taking some integer points, we also need to take some scores between -1 and 1 to distinguish the relative positions of the graphs. For example, when I am in a list, in addition to taking integers such as -3, -2, -1, 0, 1, 2, and 3 as independent variables, I also take positive and negative half, so the corresponding function values are positive and -1/8. Since when x is equal to half, the third power of x is equal to 1/8, and the second power of x is equal to 1/4, therefore, when x is equal to half, the point corresponding to the image with y equal to the third power of x is below the point corresponding to y equal to the second power of x. So I can draw the function graph more accurately. Furthermore, please note that y is an odd function equal to the third power of x. Regarding the symmetry of the origin, we can also first draw the image of the force in the first quadrant, and then draw the image of the force in the third quadrant based on the symmetry. Next, we will analyze that y is equal to the power of half of x. Since y is equal to x half power, it can be written as y is equal to the root x. X is the square root, so x must be greater than or equal to 0. In this way, we obtain its domain as a left closed and right open interval from 0 to positive infinity. Due to the fact that the domain is not symmetric about the origin, it is a non-odd and non-even function, and the independent variable can start taking values from 0. If x is equal to 0, quarter, half, 1, 2, 3, 4, 9, then the corresponding function values are 0, half, and half with root numbers 2, 1, 2, 3, 2, and 3, respectively. Draw corresponding images by tracing points. This is a curve that starts from the origin and falls within the first quadrant. We have obtained graphs of 5 power functions. Please remember the shapes of these 5 power function graphs. In addition, special attention should be paid to their relative positions in the public area. For example, in the range of 0 to 1, from high to low, y is equal to the negative first power of x, y is equal to the half power of x, y is equal to the first power of x, y is equal to the second power of x, and y is equal to the third power of x. On the interval from 1 to positive infinity, from high to low, y is equal to the third power of x, y is equal to the second power of x, y is equal to x, y is equal to the half power of x, and y is equal to the negative first power of x. Next, Please observe the graphs where y is equal to the third power of x and y is equal to the half power of x. Based on the function analysis, write down the conclusions you have found in the table below. After you finish writing, we will check them one by one. Y is equal to the third power of x, its locality and value range are both r, its parity is an odd function, and its monotonicity increases monotonically on r. Next, let's take a look at the left closed right open interval where y is equal to half the power of x, and its locality and value range are both from 0 to positive infinity. Its parity is a non-odd and non-even function, and its monotonicity increases monotonically over a left closed and right open interval from 0 to positive infinity. In this way, we obtained graphs of 5 power functions and their respective properties. So please consider, what are their common properties? What are the different properties? You can observe from the following perspectives. 1. Common points in the distribution area of the image. 2. Symmetry of the function. And 3. Trend of function changes. By observation, we can find that all 5 functions have images in the first quadrant, and the images in other quadrants can also be obtained through symmetry. Therefore, we can focus on the images in the first quadrant. By observation, it can be found that all 5 function graphs pass through points 1 and 1. This is their commonality and also their invariance in change. Since any power of 1 is 1, we can also verify it from an algebraic perspective. Next, let's take a look at their differences from the perspective of symmetry. First, y is equal to x, y is equal to the third power of x, y is equal to the negative power of x, which is an odd function, while y is equal to the power of x2, which is an even function. You can see that when the exponent of a power function is odd, the corresponding power function is odd. When the exponent is even, the corresponding power function is even. Is this a coincidence or an inevitability? Interested students can continue their research after class. Next, let's take a look at monotonicity. On the interval from 0 to positive infinity, the function y is equal to x, y is equal to x squared, y is equal to x cubed, y is equal to x half power monotonically increasing, and y is equal to x negative power monotonically decreasing. By observation, it can be observed that on the open interval from 0 to positive infinity, when the exponent alpha is greater than 0, the corresponding power function monotonically increases. When alpha is less than 0, the corresponding power function monotonically decreases. Is this a coincidence or an inevitability? Interested students can also continue their research. In addition, when alpha is less than 0, there is another characteristic. In the first quadrant, the graph of the function y equal to the negative power of x is infinitely close to the y-axis upwards and infinitely close to the x-axis to the right. In this way, we have summarized the properties of the function through its graph. As we all know, the conclusion obtained through observation is a visual judgment from a graphical perspective, and we still need to rigorously prove it from an algebraic perspective. Can you prove from an algebraic perspective that y equals the root x and is an increasing function? To prove that y equals the root x is an increasing function, that is, to prove that y equals the root x monotonically increases over a left closed and right open interval from the domain 0 to positive infinity. Firstly, we take two values x1 and x2 within the domain, where x1 is less than x2. Next, we compare the sizes of fx1 and fx2. When we are relatively small, we often use the method of subtraction, where fx1 minus fx2 equals the difference between the root x1 and the root x2. Since there is no theoretical support to determine the size of the root x1 and the root x2, we need to modify this equation. For this type of deformation with a radical, we often use rationalization methods, and here we use molecular rationalization methods. The numerator and denominator are multiplied by the root x1 plus the root x2 at the same time, so that the numerator becomes x1 minus x2, and the denominator is the root x1 plus the root x2. Since x1 and x2 are both greater than or equal to 0, and x1 is less than x2, we obtain that the numerator x1 minus x2 is less than 0, the denominator x1 plus the root x2 is greater than 0, and the overall fx1 minus fx2 is less than 0, that is, fx1 is less than fx2. For any x1 or x2 in the domain, when x1 is less than x2, f1 is less than fx2. Therefore, we can determine that fx is monotonically increasing with the root x in the domain, and we can say that fx is an increasing function with the root x. Next, we will summarize the knowledge of this lesson. Firstly, by abstracting real-life examples, we derived the concept of a power function, which describes a function where y equals x to the power of alpha. We call it a power function, where x is the independent variable and alpha is a constant. Improved mathematical abstraction skills during the process. Next, we obtained the domain of the function based on its analytical expression and used the point drawing method to draw the function graph. In our high school stage, we need everyone to master the graphs and related properties of these 5 power functions. Everyone should pay special attention to the relative position of images in the public area. Okay, next we will analyze the properties of the function based on its graph and analytical expression. By clarifying the locality and range of functions, when discussing the parity of power functions, we found that when the exponent of a power function is odd, the corresponding power function is odd. When the exponent of a power function is even, the corresponding power function is even. When discussing monotonicity, we find that when the exponent of a power function is greater than 0, the corresponding power function monotonically increases in the open interval from 0 to positive infinity. When the exponent alpha is less than 0, the corresponding power function monotonically decreases in the open interval from 0 to positive infinity. In addition, we also found a commonality among them, that the graphs of the 5 power functions all pass through points 11, and the characteristic that y is equal to the negative power of x. We used the graph of functions to study their corresponding properties, and conversely, we can also use the properties of functions to assist in drawing. That's all for today's class. Goodbye, everyone.